12 years ago, I made my last update on the state of my Mario 64 build in Blockland. This was my second attempt at building this by hand, with the help of friends and community members of the game. I'm grateful for everyone involved who wanted to share my experience of having a recreation of Mario 64 in a game like Blockland. However, like my first attempt, this save was lost, and because it took so many months to even get the interiors just right, I decided to call it quits. It was time to focus on other aspects of my life. What you may not know about me is that I took an interest in computers at a young age. This morphed into an interest of pursuing computer science at the college level to get a better grasp of how and why software was made in the first place, and what could be done to make it faster, more reliable, and enjoyable to use. This interest took hold of me so much that I made it as far as getting a master's degree in the subject with an emphasis in computing systems. With this arsenal of knowledge, I found a way to revive this project and many others that were planned by myself without needing many months or years of careful crafting. This is the story of how I instead spent many months of understanding, transforming, and verifying my findings to make a tool that converts a 3D model into Blockland bricks called Schematic to BLS. To figure out if this was even achievable, I had to see first whether it was possible to make bricks outside of Blockland. There are many aspects as to why it had to be done this way, which will be addressed later, but one of the main reasons was to ensure that I had a program that was not dependent on Blockland's scripting system. This is crucial since Blockland itself is a 32-bit application, meaning that I have to deal with some limitations, such as only being allowed up to 4 gigabytes of memory, which can be problematic given the size of some of these models. With that addressed, I chose to make this an external application, specifically written in Rust because I happened to be learning it at the time and wanted more practice using it. Because it was decided that we would be looking at Blockland from the outside, it was important to understand the rules behind placing bricks. These rules often define the game's coordinate system, which dictates how something is placed next to something else, whether to the left or to the right of it, above it, below it, etc. Fortunately, Blockland stores what bricks exist and where in a BLS file, where BLS stands for Blockland Save. Unfortunately, the format of the save file is not well documented, and I do not have access to the source code of Blockland to cheat and learn the underlying logic, so it was time to do some detective work. The objective with this investigation was to figure out the minimum knowledge needed to place one or more bricks in a valid BLS syntax, where syntax represents the rules and patterns by which data, like words, are formed in a language. So, to get started, I went into Blockland and made many saves consisting of common brick arrangements, like having a brick alone, or 2 bricks next to each other, and 2 bricks stacked on each other, even exploring different brick sizes with these variations as well. These gave me a baseline to find any common patterns amongst all these simple save files, such as learning that all of the files start with a header of some kind that does not change no matter what you save. After noting that down, I learned that in the save file, there is a line indicating how many bricks I had in the build. And then following that were lines of syntax that represented what bricks I placed, which I could not fully comprehend at first. Luckily, someone on the Blockland forum posted a public resource about their understanding of the BLS file format, which helped fill the gaps of my understanding. With all this knowledge in mind, I went ahead and wrote some code that would automate the process of placing any number of bricks. First, I fleshed out the process I had in mind for converting a collection of bricks into a save file, writing it out in pseudocode so that I could focus purely on the logic at the high level. Then, I translated each section of pseudocode into actual code, filling in the details necessary to make each section work as intended. Finally, to be sure that everything was correct so far, I wrote some checks called unit tests to see if a hypothetical set of bricks would match a particular save that I made earlier. Unit tests, and later integration tests, ultimately granted a massive boost in efficiency, and with confidence that I was on the right track, I would not need to manually check Blockland along the way for every one of my changes. Part of what makes recreating an environment in a game like Blockland is that it closely resembles sculpting in a few key ways. The type of material often dictates how the chiseling will be done when it comes to detailing some structure, where in this situation, We are coming from a model consisting of lines and curves, trying to form a structure in an environment that only knows of lines in the form of cubes, so some estimating is necessary, since a one-to-one mapping is not possible. Estimation, when done well, can create beautiful recreations such as Bones 4's Titanic project, capturing nearly all of the details of the reference as much as possible. However, it can also be very time consuming, especially when trying to compare and contrast all sorts of bricks that can be used to make some section of the recreation more or less accurate to the original. Doing this alone, I wanted to find a way to shave off as much of that time as possible, and I eventually found just the right tool to get me started. What even inspired this project to happen in the first place was the discovery of a 3D mesh voxelizer tool called BinVox. From the website, BinVox is a program that reads a 3D model file, rasterizes it into a binary 3D voxel grid, and writes the resulting voxel file. This tool essentially looks at a model, finding whether each point of it is filled with something based on our desired resolution, and collects these points, calling them voxels. Voxels are often reconstructed with cubes, which is how this tool is known to have some interesting use cases in Minecraft. In fact, it was so popular that the tool itself supports exporting whatever it generated into a Minecraft schematic file. There's an important reason why it is great that this exports to this file format, specifically having to do with the relationship that Minecraft has with Blockland. Minecraft's worlds are constructed with blocks, which are essentially just cubes exclusively of just one size. Blockland happens to have bricks in the game that are equivalent to Minecraft's blocks called cubes, and there's 5 different types by default, which are 4 times cubes, 8 times cubes, 16 times cubes, 32 times cubes, and 64 times cubes, meaning that I have options of scaling. So, with this mapping of blocks to cubes, and knowing that a Minecraft schematic file makes it easy to get this information I need to build a model automatically, such as the size of the area, and whether a block exists in the area or not, I went ahead and decided to treat this as the input to the entire program, thus deeming the name schematic to BLS. With these endless possibilities, this felt feasible and a little too powerful, but there were problems I had to address. At the time of recording, the default brick limit for Blockland when launching in the custom game mode is 262,144. This can be changed by the player if they wish, but that will only max out to the true limit recognized by Blockland's UI, 1,048,576 bricks. This can be a problem because the free edition of BinVox allows for transform models up to 5 tile length, 5 tile width, and 5 tile height voxels. And if you do the math, that's a maximum of 134,217,728 voxels. And as a reminder, a voxel is treated as a block in Minecraft, and a Minecraft block maps to a Blockland cube brick. We want to minimize the amount of bricks we use just in case someone evil decides to do a full 5 tile length, width, and height render and see what happens within Blockland, which I can assure you, the result can be deadly. So, how do we work within this limitation? I happened to find a solution in a place on the internet where all programmers go to test their skills, often for interviews, LeetCode. LeetCode is a website where people come together to solve various programming challenges, ranging from easy to hard. I happen to use this website as a valuable resource to practice problems presented in my graduate algorithms course, my last course needed to graduate with my master's in computer science. One of the first topics they teach in the course revolves around dynamic programming, which is a way of designing algorithms where a problem is broken down into simpler subproblems, where each subproblem's result is used to build up to the original problem's solution. Coincidentally, the particular dynamic programming problem on LeetCode that helped this issue right away is called the maximal square problem. Maximal square describes a situation where you're looking at a lot of squares of the same size in some area, trying to figure out if you can find the largest square if you were to combine some of these smaller ones together. How one uses dynamic programming to solve this problem is by shrinking the area down to the smallest it can be, noting what would happen if you solved it yourself, and gradually increasing the area, jotting down noticed patterns. For this problem, the patterns of interest are that there can be only one square, or two next to each other, or overlapping each other if multiple pieces are in play. A maximal square is made when if you look at the squares behind it, whether to the left, bottom, or diagonal left, if all of them are filled, then we found a bigger square, noting the length. The good news about maximal square is that it is applicable to our situation here of trying to find the least amount of bricks, albeit needing some modifications. First, maximal square is great if we were dealing with 2 dimensions, but since we are in a 3D environment, we want to actually change this into a maximal cube, which is not too hard to do. All that needs to be done is checking for depth now, noting what squares are on our same level and one below. Secondly, by default, this problem only returns the largest cube found, but we want to utilize all possible largest cubes, since the more large cubes we can find, the less amount of bricks we have overall, consuming smaller cubes that would otherwise be redundant. So this should be simple. All we have to do is repeat this method of finding largest result, marking off what we've found, and repeating until everything has been seen, right? When I hooked up what I had so far, it took me 15 minutes to figure out there was at least one issue with translation. It was not 15 minutes of reflection, but 15 minutes of waiting for the program to finish executing, which is a big problem. If I want to find out the source of the translation problem, the last thing I want to do is wait 15 minutes for each repair attempt to see if it works. While I do have unit tests, they only serve as checks for correctness, not efficiency. Therefore, another tool had to be introduced to gain some insight on what was making this process take so long: a profiler. A profiler in computer programming is a tool used to take measurements on some running program, such as gathering the number of calls of specific functions or program code lines. Using a profiler is important in this situation, since a program that is running slow is often a program that is doing a ton of work, often unnecessary work. Figuring out where that is taking place is vital to understanding what needs to be fixed, keeping a developer focused on what actually needs optimizing. The specific profiler I used generated a visual called a flame graph, where it shows how often a profiler checked in, called the number of samples collected, and where the profiler was found in the program when checking in. This flame graph showed that searching over and over for the largest cube was taking up the most amount of time, and it was because of a massive oversight that software developers are expected to know. The runtime of solving maximal square with dynamic programming is big O of length times width, where runtime means the number of steps taken while the program is executing, and the big O represents the worst case scenario for the total amount of steps needed to run a program. It is this way because we are looking over all the squares in the area, and our area can either be a square or a rectangle. This is important because this dictates how fast a program can run overall, and the higher that number within the big O, the longer it will take for the program to be finished. To show the pain of a software developer who knows a big O, imagine you were responsible for finding the largest square, and I suddenly gave you an amazing response time of 0.01 seconds, but I decide that you'll have to look over an area of 512 by 512 squares. If each square you check and add to the total count takes exactly 0.01 seconds, and the number of times you'd have to do this is 512 length by 512 width, you're looking at spending at minimum approximately 2,621 seconds, or about 44 minutes if I force you to look at every last square. Now imagine we were doing this for cubes, where now the runtime includes height, meaning that the big O is now big O of length times width times height, and the height is 512 as well. Now it'll take you approximately 1,342,177 seconds, or 22,369 minutes, or 372 hours, or about 16 days. This gets worse when considering that the naive way of finding the largest cube involves looking over all the cubes we've recorded, which is once again big O of length times width times height. But because we want all largest cubes, we run into a situation where we may very well be doing this for every cube we've recorded, making the runtime now big O of length times width times height times big O of length times width times height, or big O of length squared times width squared times height squared. This isn't good, so how do we work around this? The answer lies in considering that we are dealing with a search problem, and there is a data structure that comes in handy for making searches like this easier. Before I talk about a max heap, it is important to know what even is a heap in the first place. Imagine you have a pile of, say, clothes, and each of them has their own value to you. If you wanted to get a piece of clothing with the highest value, then a normal pile would not do, since you would have to search through it entirely to find what you seek. What if instead there was a way to organize the pile such that the most valuable clothing is always at the top, no matter whether you pull from it or not? That is the idea behind a heap, where it is a collection of items often in the form of a binary tree. And however we decide to determine what gets pulled from the top of it dictates whether it is always the highest, making it a max heap, or always the lowest, which makes it a min heap. A max heap is helpful when you're reducing our runtime when it comes to finding every largest cube when designed in a very specific way. When looking for every largest cube, it is important to note where it was found in order to know where to place it overall. If we assume that every largest cube can be placed, then we can produce a pile of all possible largest cubes with their potential sizes and locations. If all these possibilities are added into a max heap, then it makes it easy to find the maximum largest cube from this pile so far, and every subsequent one that follows. In fact, easy in this case turns the runtime of searching for every possible largest cube from big O of length squared times width squared times height squared to big O of length times width times height times log base 2 of length times width times height, which is close to ideal since for every cube we visit, we can quickly look up the largest one right away, rather than having to compare against every other cube. The big O of log base 2 of length times width times height portion of the runtime stems from how a heap is organized in the first place, where I mentioned prior that it is based off of a binary tree. A tree is a type of graph, where each graph has a series of nodes serving as the items of interest and edges representing the relationship between the nodes. What makes it a binary tree is that a node can have only up to 2 edges coming out of it. That's why the number 2 is found in the runtime. It is a logarithm because whenever we have to repopulate the heap when we pull the highest item, we are not exploring the entire tree, only a branch of it, which at worst is the height of the entire binary tree because of the rule that any node above me must be a value higher than I. One more important detail comes from how we want to claim each largest cube. While a max heap certainly makes it much faster to get all the largest cubes, we need a way to ignore other possible largest cubes if the maximum we currently find consumes them. Because a max heap is a type of graph, we can borrow the technique of marking nodes as visited, which is part of the popular methods of looking over items in a graph, like breadth first search and depth first search. Since each node is a possible largest cube with its size and position, whenever we claim the maximum largest cube so far, we can safely assume that each neighboring cube from the position we have of the maximum has been claimed now, meaning we can skip them for future consideration, reducing the amount of work we have to do in the long term. Underneath a game consists of its own coordinate system, dictating where objects are placed in its world. Knowing which coordinate system is in use is important for this task because Blockland and Minecraft have different rules stemming from their respective coordinate system when it comes to placing blocks. For Minecraft, since all blocks are the same size, all we really need to know is how each block is stacked. In this case, Minecraft represents the height by the y-axis and the length and the width by the x and z axes accordingly. When it comes to checking if a block is in place or not in the schematic file, the formula to get this is y times length plus z, all multiplied by width plus x. In comparison, Blockland is different in two ways. First, the coordinate system in Blockland follows the one provided by the Torque game engine, since Blockland was created from it, meaning that the z-axis represents height and the x and y axes represent length and width accordingly. This means that we will have to adjust the way we check if a block is in place, which can easily be done since we can flip the axes to match the other game. Secondly, Blockland's bricks can vary in size, so now it's important to figure out how the size of each brick influences how they are placed. Earlier, I mentioned the significance of how I also created integration test, which is a check where the output of the whole program is tested and verified versus just the individual pieces. I explicitly made these tests to discover what I had in store for figuring out what math I would need to do to honor Blockland's coordinate system, especially since I did not have much reference or access to the source code for Blockland. So, with each of these tests, I tried to predict what formula Blockland used to place cubes, using something called linear interpolation, which is the process of estimating a value inside each set of data points, which in this case, each brick's position made from Blockland was used as my set of data points. The most famous type of linear interpolation is finding the slope of some line in algebra, which is what I used, where one calculates the value in between 2 points to find the midpoint to derive a formula in slope-intercept form. After some trial and error with interpolation and asking some of my fellow engineering friends, I eventually discovered three factors going into a brick's position. First, when reading over a Blockland save file, each coordinate of a brick represents the center of that brick model, meaning that if I found a cube of size 4, then I would essentially divide that by 2 to get its center point, at least for the x and y axis points. Second, in relation to the last point, a brick's height follows that rule for the z-axis mostly, except that height is defined by the number of flat bricks one has to stack on top of each other to fill the brick's height, which is 0.1 per flat brick. Finally, the size of the first placed brick influences the offset of all the other bricks that follow it, where by linear interpolation, the math comes out to dividing the size by 4 for Blockland, and this caused one major problem. Blockland has different levels of precision when considering the x and y axes and the z-axis respectively. For the x and y axes, all brick positions can go up to 2 decimal places, yet the z-axis only goes up to 1 decimal place. This is not a problem when considering cubes starting at a size of 2 and going upward, but becomes a major headache if one wants a 1 times 1 cube. After considering offsets, the math comes out to say that the height must be 0.25, but the game will not honor that height, either making it 0.2 or 0.3. This is why Blockland does not have an add-on for making a 1 times cube, where instead you get a 1 times stud, which is slightly too tall, which has a rippling impact on how everything else is placed above it or below it. The closest I could find to making a 1 times cube is an add-on that builds one by splitting it into 2 alternating pieces, where you can replicate the height of a 2 times 2 cube and onward, but you still do not get a 1 times 1 cube itself. This took me 2 months to figure out that this limit cannot be worked around unless I patch Blockland itself. I do not wish to do that. So, as a compromise, I made 2 decisions. First, while I have kept the math just in case Blockland makes that accurate one day, I've limited the set of all Blockland cube sizes to be between 2 and 64 inclusive. Last, but not least, when one runs schematic to BLS by default, all cubes coming from Minecraft will be interpreted as 4 times 4 cubes in Blockland, which I found to adequately represent a 1-to-1 scale of the model being converted. If anyone has a workaround, I accept contributions, since this whole project is open source, where it can be found on GitHub here. With everything hooked up and my tests passing, it was time to see how it actually looked like in Blockland. So, I fed the model of Peach's Castle from Mario 64 into the program, waited for less than 3 seconds for it to finish, copied over the save file into Blockland, and then booted up the game and loaded it. The result? Not all the bricks were loaded successfully, since there were holes in the build. What caused the holes to show up in this save? Turns out, there were cases of bricks colliding with each other. Blockland does not allow this even in normal builds, so the result was to ignore those 2 or more bricks overlapping with each other. Despite all of my written unit integration tests passing, there were certain situations unknown to me that would still cause problems. Because of this, I had to spend another month figuring out the issue, most of that time utilized in setting up a powerful technique that I learned during my course in software analysis and testing called delta debugging. Delta debugging is a technique that automates the scientific method in a debugging environment, where an input serves as the hypothesis and is further refined for every iteration of this algorithm until all possibilities have been explored. I chose this technique because I wanted to figure out the smallest input necessary to still cause holes, and I wanted to do this quickly without burning myself out doing this by hand. To make this as productive as possible, I wrote a Windows-only program that brought me all the way to checking the number of bricks loaded for some save I just generated, where if the amount of loaded bricks did not match the expected total, then that implied there were holes somewhere. In addition, while there exists an implementation of the delta debugging technique, this was written in Python 2, which is no longer supported, so I had to convert this to Python 3 before getting started. With everything set up, it was super quick to find the issue, right? Well, yes, but not because of delta debugging. What I have not mentioned about my program written for delta debugging is that it takes a minimum of 10 seconds to check if there are holes in a Blockland save, because this program simulates opening up the application and typing in commands as you would with a mouse and keyboard, which was done out of necessity since Blockland by default does not tell in its logs when a save is finished loading. In addition, my input was the model as is, which contained a minimum of 200,000 lines, And while delta debugging tries to be as efficient in its refining via splitting the input in half when it can, that is a lot of time that it needs to finish all of its possibilities, or a possibility can be a single line. I started the program sometime around 4 p.m., and it was done by 8 a.m. the next morning. However, by then, the moment I was getting ready to go to sleep, I figured out the issue by myself. Cubes can overlap each other in the largest cubes algorithm. This can happen when dealing with two cubes with at least one corner overlapping another, looking something like this. If the bottom left cube happens to be chosen as the largest, the top right cube has not been adjusted in any way, keeping what was previously deemed the largest at that point, which would be incorrect, causing an overlap in Blockland. If one were to only ask for the largest cube, then this issue is hidden, since the rest of the largest cube possibilities are tossed once the largest is found. However, because we want all possibilities, we have to address this, and luckily, it involves a slight change to how we keep track of what was claimed already. The solution to this issue stems from how we keep track of what has already been visited when populating the binary heap, the structure responsible for giving us all largest cubes as is. If I happen to choose a cube where there's an overlap with another, an overlap means that at least one smaller cube has already been visited. So, what if we backed up and made an adjustment to the current cube being claimed, where we shrink it down to the next lowest cube and try again? Turns out that worked very well, making all the holes vanish. It took me about an hour the next morning to make this fix in comparison to the delta debugging program, and while in this situation I beat it to figuring out the problem, it is nonetheless an option to utilize in the future if I need it, ideally if whatever I'm testing can be done instantly versus taking at least 10 seconds per attempt. Finally, I've gained back some time making my Mario 64 project creating this tool. Turns out, this works for nearly any model you hand it, so as long as it can be handled by Binvox or it is a Minecraft schematic file consisting of only stone blocks for now, meaning I can pursue other projects I had in mind. While I am happy to share these creations, I realize at the time of recording, Blockland does not have a lot of people playing it anymore, so it may be too late to try out some of these projects involving minigames for others to enjoy. Though, what if I told you that this can be adapted to run in Bricadia, the spiritual successor of Blockland in development? Turns out, all you have to do is run this tool, feeding it any Blockland save, including what my program spits out, and suddenly, you have all of this recreated in Bricadia instantly. While this has been a blast, there's more work to be done. All models converted using my tool do not consider colors, making it truly like one is carving from a stone to make this model in the game. This was done on purpose to try minimizing the amount of bricks needed, since colors would take a lot of these opportunities away. However, I am open to making this program consider colors as best as it can if that is something the community wants. In the meantime, feel free to use schematic to BLS for your own creations, with a link in the description of where you can download this for yourself.